Welcome and hello. This is a video tutorial on HEC HMS, and in this lesson, I'm going to be talking about subbasin transform method, specifically the kinematic wave transform method in determining runoff from a subbasin. All right, what I have on the screen here is a watershed, and I'm zooming out real quick, and now I'm going to zoom back in because I only need one subbasin to discuss in this lesson. So I'm going to use this subbasin right here. It is subbasin 6. And I've got it selected here in the basin model, as well as over here in the Watershed Explorer. Down below in the Components Editor, I now have the Subbasin tab, as well as a Base Flow tab and Options tab. Subbasin tab here has a transform method. And if I select that, I've got my options. And what we're going to talk about in today's lesson is this kinematic wave option here. So if I select kinematic wave, I have a whole bunch of new tabs in the components editor. As you see, we have a plane 1, plane 2, subcollector, collector, and channel. I'm going to be talking about all 5 of these new tabs and the parameters in this lesson in that order. So what we just described is sort of moving up from smaller to larger. Precipitation falls on the planes, and then it slowly works its way down to subcollectors, where they then flow to collectors, and that flows to a channel. First, a quick word about the kinematic wave transform method. This method is primarily designed for urban areas. There are 2 planes, a plane 1 and a plane 2, and they would be designated as impervious or pervious for 1 and 2. So what I'm going to do is I'm going to say plane 1 is for impervious and plane 2 is for pervious. So that's just, it's good to kind of keep in mind which one is which, because if we do happen to be using a different subbasin method for canopy, surface, or loss, we will not just have one tab for those different methods. We'll have 2, one for impervious and the second one for pervious. I'll show you what that means. So for canopy, I'll just go ahead and select dynamic canopy. And now we have a canopy 1 and a canopy 2. And we have to provide information for both canopy 1 and canopy 2, assuming that there's a little bit of pervious and impervious area in our subbasin. I'm going to toggle that off though. So I'm going to go up to subbasin, turn the canopy off. For surface method, if I select the surface method, now we have a surface 1. And I need to remember the data here is only for the impervious, and then surface 2 would be for pervious. But we need to enter some data first before that shows up. Okay, so let me go back to subbasin, toggle that off. There are now 2 different levels, 2 rows here of tabs, so don't let that confuse you. The kinematic wave equations are used to calculate runoff for each plane, and then a weighted composite runoff is calculated using the percentage of the impervious versus the pervious of each plane. The HMS Technical Reference Manual goes into more details about this kinematic wave transform model. So for instance, we're seeing some equations here regarding a one-dimensional approximation of momentum. And then below that, we're seeing Manning's equation for flow rate. So if you're familiar with Manning's equation, we're going to see some of these parameters required for us to input, such as roughness coefficient, the cross-sectional area, the slope, and so on. So I'm not going to talk about this too much, but if you want more information, I'll leave a link to this in the description to the video, and you can check that out. Next, let's talk about plane 1 and plane 2 at the same time. Remember, I'm going to say plane 1 is for impervious and plane 2 for pervious. The length here represents the average flow length the runoff has to travel from where precipitation falls to where it enters a collection gutter or channel. Now, when I say collection gutter or channel, it really just means the next layer up. So that would be the subcollector. So I'll just type in a number here. For impervious, I'll say 30. And then for pervious on plane 2, I'll say 50 feet. Sure. All right, back to the impervious. The slope here is in a decimal format. It's the average slope along the flow line from the point where precipitation falls to where it enters the subcollector. So I'll just type in an average slope here of 0.01%, say. And then for the pervious, I'll say it's 2%. Sure. This is for the entire subbasin of pervious area. And then this is for the entire subbasin of the impervious area. Next, we have a roughness coefficient, and this is the roughness coefficient will be higher for pervious plane than and lower for the impervious plane, of course, because for impervious, we're talking about the streets, parking lots, maybe a roof, anything where the water just will not infiltrate. So we could say something like 0.015. This is the parameter that would most likely have a lot of variation between plane 1 and plane 2. So for roughness here, I could say 0.06, say. This would represent your grass, your parks, your open space, undeveloped land. Okay, next we have percent area. This represents the area in the subbasin that is pervious. So I'll say 70%, and then I'll say 30%. So the sum of those two areas would have to equal 100%. Last, we have a routing step. The default value here is 5, and I'm just going to leave it at 5. The user's manual says that this value is used as a hint to the program when it determines the correct distance step to use during runoff calculations, and that it's used sort of as a calibration number. All right, so plane 1 and plane 2, the impervious and pervious runoff makes its way to the subcollector. And then the fields here in the subcollector tab are the exact same fields as we're seeing here in the collector tab. So I'm going to just talk about subcollector, but know that it's the same data that we're going to be putting in collector. The subcollector itself would probably represent like the curb gutter, like along the side of a street, or if there are no curbs or gutters, there may be like a small little drainage ditch along the side of a roadway. And then the collector would be a larger conveyance method for stormwater runoff, and that would represent maybe a lined canal where multiple curb and gutters flow into a collector. So just think of the size increasing from the plane to the subcollector to the collector to the channel. Okay, let's talk about subcollector, and then I'll talk about briefly how the values for a collector relate to the subcollector values. Starting with length, the length for the subcollector is the average distance from the beginning of the subcollector to where it enters the collector. So I'm just going to throw in a number here. I'll say 300 feet. The slope, again, this is sort of approximated using maps or survey data, but I'm going to say this is 0.5%. The Manning's roughness coefficient here, N, we saw that in some of the equations. That is based on the material and the roughness of the surface. I'll say 0.23, and this value should, again, be an average for all of the roughness in all the subcollectors for the subbasin. Next is sub reaches, and this is used basically as a calibration parameter, similar to what we saw for the planes 1 and 2. The area here is in square miles. I'll say it's 0.085. This area is used to basically count how many sub-collectors there are in the subbasin, because we have an area for the subbasin. And then if we divide that by the number of the area for the average sub-collector, we could get a number of sub-collectors. This area is used to determine how to apply the composite outflow from the subcollector to the collector, basically the number of subcollector channels in the subbasin. Next up, we have the shape of the subcollector itself. So our options here is circle, deep, rectangle, trapezoidal, and triangle. So whatever option you choose for a shape, you'd also have to include the parameter to define that shape size, such as diameter for circle. For rectangle, you need a width. For trapezoid, you need a bottom width and a side slope, and then for triangle, it's a side slope. In the case of side slope, it's asking for the number of horizontal units for one vertical unit. So you may just go 1 to 1 would be 45 degrees. But if it's a very shallow slope, you could say it might be like 10 to 1. So that's how that works. I'm going to select trapezoid, and I'll say it's 1 foot bottom width and a 1 to 1 side slope. This cross-sectional shape of the subcollector and of course the collector will be used for the flow rate in Manning's equation for determining that runoff. All right, so that's it for the subcollector. The collector has the same parameters, but will have different values. The length here is probably going to be longer than the subcollector length. The collector slope is most likely going to be either the same or maybe a little bit less than the collector slope. Manning's N, that could be it could be about the same. Number of subreaches, I'm not sure about. The area is definitely going to be larger because subcollectors flow into collectors. And then whatever shape you select, the dimensions for that shape of the cross section for a collector will be larger than a subcollector. The last tab to discuss here is channel. So the collectors flow into the channel. And this is sort of the lake, the river, the ocean, the final stop for the stormwater discharge. And we have some of the same parameters here, but a few new ones as well. For instance, one new one is this first one, route upstream, yes or no. Typically, the answer would be no, and that refers to no upstream inflow entering the subbasin. But if we do happen to say yes, that would mean that there is upstream inflow entering the subbasin. If we select yes for the route upstream, then two fields down here, the length, this would be a little bit longer. It would be the distance from the upstream boundary of the subbasin to the basin outlet. And like I said, that would be longer than if we had said no here to route upstream, because in that case, this length would be the distance from the channel concentration point to the subbasin outlet. The routing method here, I don't want to skip over this. The options are kinematic wave or Muskingum. Now, kinematic wave is the default value here that's selected, and that's fine. The plane 1 and plane 2 will always use kinematic wave. However, the routing method selected here on the channel tab is going to be applied to not only the channel, but also the collector and the subcollector. So just keep that in mind. Again, the options are kinematic wave or Muskingum. Let's just stick with kinematic wave, and if we do, we'd also have to specify the number of subreaches as a parameter, which we've seen before. If you choose Muskingum, that field goes away. Length and slope, we've seen these before. The length is, we've already mentioned that with regard to the selected upstream method, yes or no. And then the slope, again, this can be determined using maps or survey data. It's just the average slope of the channel along the length of the channel. And this is for all channels in the subbasin. It's not just one channel, so keep that in mind. Subreaches, again, that's the same calibration parameter. And then Manning's N, we've seen that before. It's based on the roughness of the channel, of average channel in the subbasin. And then the shape, same thing. Select your shape and then go ahead and provide the dimensions for that cross-sectional area based on the shape that you selected. Well, that's it for this lesson. We talked about subbasins, transform method, and specifically the kinematic wave method for using planes, subcollectors, collectors, and channels to route water using some open channel flow types of equations to determine the runoff from a subbasin.